Hey folks, welcome back. Part two, we're walking through an example problem of a redox titration, and we've gone through the entire region up until the equivalence point. So our reaction again is iron 3 being reduced by copper 1 to make iron 2 and copper 2. Okay, so we're going to pick up now at the equivalence point in which we've added just enough copper to completely react with the iron 3. By definition, right, that's what the equivalence point is. Okay, so um, in in reality, that these do not really go to zero, right? It is still in equilibrium, so there will be some tiny amounts of copper 1 and iron 3 still present. It's not really zero, okay? But we can make a statement about their relationship, the relationship of these. If they're not zero, but we're gonna show that they are actually equal to each other. Whatever it is, they have to be equal, right? Because we've added 2 millimoles of iron 3 and 2 millimoles of copper plus. So if we could create a model, right, where we say, let's say they completely react and make all product, right? All product is formed. And then due to the equilibrium, a little bit of copper and iron 3 will also be produced in the reverse reaction. So because of the stoichiometry and everything here, we know that the amount of iron 2 and the amount of copper 2 that have been produced at this point are equal to each other. And therefore, the amount of copper and iron 3 that's left over must also be equal to each other. Okay? So think about that logic for a little while if that doesn't make sense right away. But we know that the concentrations of the products are equal because they have to be formed together, right? Anytime an iron 2 is formed, a copper 2 is also formed. And then because we've added equal amounts of iron 3 and copper, then whatever's happened here, there's going to be some tiny amounts of these. They're also equal to each other. Okay, so this is going to be an important point here. And now if we go back to the two equations that we can write of Nernst, and we once again get these two equations, right? Now, we know something about these and how they're equal to each other, but we don't really know what they are. We know that the values are small, but we cannot actually solve these as they are written, but we do know that they're equal to each other, right? They're both the same as E. So what we can do a little bit of algebra here to actually solve for this. So let's add the two equations together. Right, so we're going to get 2E on the left, and then we're going to add the standard reduction potentials of the half reactions, minus 0.05916 times log of iron 2 over iron 3, and then also minus 0.05916 times the log of copper plus over copper 2 plus. And we can keep going with this. by combining the terms in the logs, right? Basically, what we're going to say is log of A plus log of B is equal to the log of A times B, right? So this becomes iron 2 plus times copper plus over iron 3 plus times copper 2 plus. Okay, and we can take this piece inside the argument where we have, I'm going to rearrange it a little bit. I'm not changing anything, I'm just changing the order, right? Because now we can see what we said before, right here in blue, that this is equal to 1 because they're equal to each other, and these are also equal to each other. So this entire thing is equal to 1, and that's inside the log, and the log of 1 is equal to 0, right? So we go back, and this whole term here is equal to 0. So now we have that 2e is equal to just simply the sum of the standard reduction of the each half reaction. But that's twice times E. So E is going to be the two standard reduction potentials divided by 2, right? Or you could say this is the average of the two, or it's halfway between them. And so that's a general case, right? So it would be something like this. But in our case, plugging in our values up here, it's halfway between them is 0.464 volts at equilibrium, or sorry, equivalence point, which is when we added 20 milliliters. Okay, so let's look at the third region. What happens after the equivalence point? So we have our reaction again. And now we're basically adding excess copper, right? And so we can see that, well, let's work through our ice table, and then we'll see why we use the copper Nernst equation. So the initial amount of iron 3 is still 2 millimole. And let's say we're going to look at 21 milliliters. So there would be 2.1 millimoles of iron. So at equilibrium, 2.1 of copper, I should say. At equilibrium, the iron is used up. There is 0.1 millimoles of copper left. And then we have 2 and 2 here. And so we have values for copper. So we will use the copper equation, 0.161 minus 0.05916 times the log of copper plus over copper 2 plus, and we have those as 0.1 over 2. And so, right, the log of a number less than 1 will be negative. So this whole term will be positive because we're subtracting a negative. So we're going to actually have a value that comes out to be 0.238 volts. Right? So we could continue with some more values. I think I'm going to skip up to, let's try 30 milliliters of copper added. So that would be 3 millimoles of copper. And you can see that this is, let's see what's happening here. So at 30, we would have 1 millimole of copper and 2 millimoles of copper 2 produced at equilibrium. You can confirm that for yourself. So plugging that in, 0.161 volts minus 0.05916 log of 1/2. And we're going to get just a little bit above E naught, 0.179 volts. All right, there's one more special point, which we can end with, which is 40 milliliters. And 40 milliliters is special because we're twice of the equivalence point, right? So this would be 4 millimoles of copper added, and we only had 2 of iron, right? So at equilibrium, we'll have equal amounts of the copper ions in solution. So the log of 1 is equal to 0. So E is equal to E standard. So E is equal to 0.161 volts. Oh yeah. So of course we could continue this as long as we wanted, but we've clearly like gone past the equivalence point, and we can stop at some point. Actually, if you think about how far you could go till like E is equal to 0, right? So the reaction is no longer spontaneous. The amount that you would have to add is probably a lot more than you think. You could try that out. So if you wanted to say, at what point is E equal to 0, how much copper do you need to add? If you get an answer, let me know, or let me know what you got, and I'll tell you if I got the same thing. Okay, so let's take a look at a summary of all this. Whenever you have data like this, right, you should probably plot it. Visualizing your data is one of the first things you should almost always do with it. So here, I've created a redox titration curve of the data that we just came up with, and we have that typical titration curve look to it. And so right here at 20, right, is the equivalence point. The voltage at this point is the average of the two standard half reactions. And if all we had was this data, and we know the copper concentration, and we know the volume of copper that we added, we know the volume of the iron that we started with, then our unknown could be found. Like we've kind of done that before, okay? But that's the idea of how we do redox titrations. If you look at the homework, you'll have an opportunity to walk through some different reactions. And there's one major piece that I left out of this entire thing, but I thought it would be easier to understand and get the point across. So I'll say that one thing now. So how do we actually measure cell potential, right? How do we measure E? Well, we need to have a reference electrode in the solution, which we can then measure the voltage across. And so a standard one would be silver. We could write it as silver chloride. And that has its own voltage of 0.197, right? Now remember, these are all relative values from the tables. So what this means, if we have a reference electrode, is that what we're actually going to be measuring is going to have to take this into account. And so when we do our calculations, every single calculation, when we calculated the E, we would subtract 0.197 from that value. Okay, this is really important when you get to the homework, and you'll see it on the homework. It'll walk you through that as well. But if we go back to here, like one of our earlier slides, we would have to add in a negative or a subtraction of 0.197. Everywhere, we would have to subtract 0.197 right here, and everywhere, right? Right here, here as well. Okay, so I hope you can understand why I left that off. It would have just kind of, I think, complicated the procedure on this first time through. But now you can think, okay, that's like just the reaction, what we just did. But how do we actually measure it? We have to have that reference electrode in there. That reference electrode is going to change the absolute value that you actually measure. And so we have to subtract that away. It won't change anything about, say, this titration curve. Other than it will shift the whole curve down by 0.197. So maybe, something like this. So take that into account when you're actually doing this for real. But the whole process is just the same. You just subtract away the reference electrode at the end. And if it's silver, it would be 0.197. If it's something else, it would have a different value. Okay, so that's going to wrap up redox titrations. If you have any questions, let me know. Walk through this as needed, slowly again. Check out chapter 16 in the textbook, and also the homework for chapter 16 will give you the opportunity to do this for a different redox reaction. So good luck. Let me know if you have any questions.